Section 4.1, Exponential Functions. Typically, exponential functions are used to model growth of any sort. It could be related to money or cells with cells growing and dividing and that sort of stuff. So here's a classic problem to kind of get you introduced a little bit. You just won a contest and some rich person wants to give you money. They give you two options. You can either take $5 million or you can take a penny today and double the amount each day for 30 days. So that would be 2 pennies tomorrow, and then 4 pennies, 8 pennies, 16 pennies, and so on. So which is the more prosperous choice? Which way would make more money? Instinctually, you probably think $5 million right off the bat. But let's go ahead and take a look at it. So here I have an Excel spreadsheet. 1 penny on day 1, so you have a total 1 penny. Then 2 pennies for a total of 3. 4 pennies brings your total up to 7. 8 pennies brings your total up to 15. So let's keep going down for a little bit. After 10 days, you'll be making, or on that 10th day, you'll be making $5.12 for a total of $10.23. Let's keep going. Here we are at the halfway point, $163 halfway through on just that day for a total of $327. Doesn't look very promising. Ooh, look at day 18. We're now up to $1,000 in just one day, but remember there's 1,000 thousands in a million. 5,000, 10,000, 20, 40. Day 25 for 330,000. There we are, day 29, over 5 million. And day 30, we make another 5 million just on that last day for a total of over $10 million. Now, just for fun, let's, so obviously that would be the better choice to take the penny doubled each day because you'll make twice as much money, a little bit more even. But just for fun, I actually found a website that shows 1 billion pennies because that's how many that would be. 1 billion pennies is about 5 stacks of pennies that are about the size of each one about the size of a school bus. So 5 school buses in pure pennies. I don't think there's that many in the world, but that's a lot of pennies if you were to be paid in pennies. It would weigh over 3,000 tons. That's kind of funny. So, more prosperous choice would obviously be take the penny. Now, that is an example of an exponential function. Typically, they look like a to the x. For our penny example, since it doubled each day, 2 was our base here. To the x minus 1 because it doesn't double until the second day, so that's where that comes from. And then since it starts with a penny, 0.01 would be our starting point. So you could actually graph that and see what it would look like. In Excel, I actually graphed it. Here's the look of an exponential function. Starts out really, really slow, which you saw day 15. It was like we were not making any money yet. But then rapidly it begins to increase. So exponential functions, some basic properties. You could plug in anything in the domain from negative infinity to positive infinity. But it would basically, no matter what, look like nothing on the until you start plugging in 0. We know that anything to the 0 power is going to equal 1, so it always has a y-intercept of 1. And then it rapidly begins to increase. So exponential functions basically look like this. The numbers can change, but they basically look like that. The domain is negative infinity to positive infinity. Range is, unless it's shifted or something, would be from 0 to infinity. There's a horizontal asymptote at 0. You won't ever actually equal 0. It always intercepts the y-axis at 1 unless it's shifted up or down. That sort of stuff. So doubling is a pretty common exponent to look at, or 2 to the x. It's pretty common to look at. And this is about 2 to the x. 2 to the x would actually cross 2, and then 2 to the second would be 4. And then it'll go up here to 8 next, and so on. So I mentioned those transformations, but here's a quick review. If you add something outside of the function to the back, it shifts it up. If you subtract it, it shifts it down. If you subtract it from the x, it'll shift it to the right. Add it to the x, it'll shift it left. A negative out in front reflects over the x-axis, and a negative in front of the x flips it over the y-axis. So here's some quick examples. If you start with 3 to the x, they have the basic shape of 2 to the x like we looked at earlier. Adding a 1 to the x will actually shift it left 1 unit. Subtracting 2 at the back would shift it down 2. A negative in front would flip it, reflect it over the x-axis, and a negative in front of the x would reflect it over the y-axis. So if it's reflected over the x-axis, it would actually look like that. If it's reflected over the y-axis, it becomes a decreasing exponential function. Also called an exponential decay. And that actually represents, like, in chemistry and things, when you talk about the half-life of some radioactive element, that's an exponential decay. So in math, there's another pretty common mathematical constant called E. It's also called the natural number or Eulers number. It's similar to pi, that they're both irrational, never stop, never repeat. They're a little bit mystifying. Pi is about 3.14159. E is about 2.71828. Most people know that pi is the ratio of circumference over diameter. Well, E is related to this function right here, 1 plus 1 over x to the x power. So if you went for infinity, if you graph that function, it would look like this, and it would flatten out. And that spot where it flattens out, you'd have a horizontal asymptote at E, the 2.71828. So here's E to a few more decimal places, 2.71828, 1828, so on. Now, what is E? It's a little bit more difficult to answer than pi, but E is the number that describes continuous growth. So if you think back to our penny example, we talked about it doubling each day. Well, in a continuous growth, you would start with something, and it's continually growing just a little bit. And this actually makes more sense when you think about money. So let's talk about money for a second. If you were talking about interest on money, you would say you had $100 or something like that. You would get interest immediately. You'd get that little bit of interest on that $100, and then immediately that money that you gained in interest would start gaining interest as well. So then you'd have more interest, and it kind of just piles onto itself because interest makes more interest, which changes how much interest you're getting. So for continuous growth, since it's a little bit more than doubling, that's why it's 2.7 whatever. That's why E comes about, and that's how E was found and calculated. So if you think about that little bit of interest that's added on, then that begins collecting interest. So for continuous growth, that's what it's about. And that's why it's this 1 plus a little bit, that little bit extra that just got created, then also creates more interest. Now, this doesn't really apply at all to our lesson, but it is interesting, and I always found it very interesting. You take E, some crazy 2.718281828, and you take the imaginary number I, the square root of -1, and pi, which is 3.1415926535589. Those crazy decimals, but e to the I pi, when you put it all together, equals -1. Just a very strange, beautiful mathematical relation.